We recognised a need for the effective treatment of wounds in the hours and days after a disaster event. Our group's aim is to provide affordable wound dressings that indicate infection and have antiseptic properties. It will decrease pressure on the limited emergency services by providing a quick and reliable treatment of common wounds. A wound dressing that gives indication of infection means the dressing has to be changed less frequently, as no need to check visually for infection, which simultaneously reduces opportunity for new infection due to exposure.
When the Haiti earthquake of 2010, tetanus was a big problem. Tetanus is a complication when disasters strike in developing countries. Collapsing structures and swirling debris inflict numerous crush injuries, fractures, and serious wounds. Clostridium tetani infects wounds contaminated with dirt, feces, or saliva and releases neurotoxins that may cause fatal disease.
The University of Bath developed a plaster in which non-toxic fluorescent light dye is released from tiny capsules in a gel-like material when the plaster comes in contact with the bacteria. We've also found that a group of German researchers developed a plaster which changes color when the pH value is between 6.5 and 8.5. However, we've decided to create a much cheaper one that can be put in survival kits in disaster zones.
As it has a colour change between pH of 6 and 7.6, it should change when the pH of infected wounds increases from 5 to on average 7. We proved this by using a pH probe and the continuous addition of a base to an acid. However, with further research we have found that neither would the wound's pH change be reliable enough nor the indicator sensitive enough to give a reliable detection of infection. When we tried to release it in an agar dish, it would diffuse to become undetectable within a few hours. Here we have an agar layer of starch covered by another of iodine. Bacteria would digest and grow through these thin layers, causing them to mix and the iodine to change from brick red to blue-black. There were several problems with this idea. Firstly, the layers were too thick for bacteria. Secondly, starch and iodine diffused through and mix, causing a colour change. Finally, for bacteria to travel through the agar, it must be nutrient-rich. However, nutrient agar contains starch, which triggers a premature colour change. We tried many options, including spraying thin layers of agar. Reflecting on the issue with iodine diffusing through the agar, we got inspirations from edible boba balls to trap iodine in sodium alginate capsules. We dissolved sodium alginate in iodine, which was then put in a cold solution of calcium chloride with starch. After a few attempts, we managed to find a way to keep the liquid inside liquidy by taking the balls out of the calcium chloride solution as soon as possible. Due to the most common cause of infection being E. coli, we tested if the bacteria would eat through the sodium alginate balls by putting them on an E. coli soup and on an E. coli lawn. They were left for over 48 hours in the incubator and we saw a change from black to colourless. This was not what we expected to happen, as our assumption was that the black iodine solution would diffuse out when the bacteria eat through, but we were able to see the colour change in the balls.
Here we have a model of a patient's arm with a wound. So they'd go to the hospital or treatment centre and we'd clean the wound, but unbeknownst to them there would still be bacteria in there, which would be represented by these two models. So the plan would be to put a wound plaster over the arm. Obviously this is a very exaggerated size, it would be a much smaller size, with a layer of agar and starch and just a layer of agar. Then these blue droplets are sodium alginate balls containing iodine and starch. So the plan would be, once you put the plaster onto the arm, the bacteria would move through the two layers of agar. They would eat through the sodium alginate balls and iodine would diffuse out, disrupting the pattern that would be visible to the patient. And here's an animation to show the same thing.
Hydrocolloid dressings are useful as they are waterproof, which is an important factor in disaster zones, while promoting wounds healing as they contain gel-forming agents. They are also semi-transparent, which is what we need to see the color changes. Polyurethane foam dressings are normally used when there is a lot of extra dead fluid. They are cheap but can maintain moist environment on the surface.
Our experiments with bromothiamyl blue and iodine in plain agar didn't work, but from this we managed to find successful alternatives, like the sodium alginate balls with iodine encapsulated. This is what we've been left wanting to find out more about. So our next step now is to develop the project as a whole, which would be to incorporate the alginate balls into a physical wound dressing.
Communication was key when it came to organising when we would have our practical sessions and to ensure that we were efficient. Once we've finalised our ideas, we've moved on to thinking about how to best present our project, such as by making a physical model and creating an animation. There was a sense of leadership, but not in an overpowering way. Thank you for listening to our presentation.